All right, so hello everyone. Um, First things first, can you all hear my voice?
Yes.
All right, thank you. So, first and foremost, apologies for the delay. We had some technical difficulties. So it's now 8. It's almost 8:20. So let's just start. All right. So good evening and welcome everyone to today's session. Um, all right, so today we'll continue on to the next topic in Introduction to AI. Today we will discuss the topic Intelligent Agents. But before that, a gentle reminder to everyone to take your attendance. And if you have any questions regarding today's topic, feel free to ask the questions in the chat box and we will try our best to answer you. All right, so now I'll pass it to my fellow tutor, Mr. Niangui, for the first part of today's session. Mr. Niangui, please.
All right, guys. Can you guys hear my voice clearly?
Yes.
Okay. Let's start right now. Okay, so today we'll be talking about the topic, which is the intelligent agent. Okay, so let's see. This is our agent and environment. So for the intelligent agent, there are some must for the agent. Firstly, the agent must be having sensors and the actuators. Okay, this is our agent and these are sensors. For example, the sensors may be like for example for the human now. Okay, human have sensors like eye, tongue, and skin and nose. These are the sensors for the human to get the percepts from the environment. What is the meaning of percepts? Percepts is actually the stuff that we can sense from the environment. For example, we can get the, for example, if you're using the eyes, we can get the percepts from the environment. For example, like what we can see from the environment. For example, if the nose, then the percept will be that the smell of the environment. Okay, so that is the sensor and the percepts. And the actuators are actually something like our arms, like the human arms, the legs, and something like that. We can use these actuators to carry out action to change the environment. For example, like we can use our leg to move, we can use our hand to like move something from A to B in the environment. So this is what called an agent. Okay. So in this case, the agent, an intelligent agent, how does it work? The process cycle is like this. Firstly, the intelligent agent will get the percepts from the environment by using their sensors. After they get after they get the percepts, they will use some sort of like the function, then they translate all the percepts into the action, and then they will perform the action into the environment, and then proceed to repeat the cycle again and again. So we get the percept from the environment, then translate it to the action, then perform the action to the environment. So this is a cycle for an intelligent agent. Okay, for example, like the chest playing board, for example, like the vacuum cleaning machine, which we'll talk about later, is something like this. Okay, intelligent agent. Okay, so this is a definition for the agent. Okay, an agent is anything that can be viewed as perceiving its environment through sensors and acting upon that environment through actuators. So this is basically what I'm saying just now, right? We use sensor to get the perception, the percepts, and then use our actuator to act upon the environment. Okay, and this is the terminology used in our intelligent agent. The percept is the perceptual inputs at any given instant, which is get from the environment. Okay, like the stuff we get from the environment. And the percept sequence is a complete history of everything that the agent have ever perceived. Like if we go from the A to the B, and the process like everything we have seen from the A to the B in the path of the A to the B is the complete history. Okay, this is what called the percept sequence. Okay, all the complete history of everything that we have seen. And the agent function is the part that I share this box, means that it will translate the percepts into the action with some sort of function, okay, which map any given percept sequence to an action. Okay. Okay, so right now we have proceed to our next part. Is an example of agent. For example, human, our eyes, ears, and organs are sensors, and the hands, leg, mouth, and other body part are actuators. We use that to perform action and use this to get the percept from the environment. And also we got the robotic agent. In this case, the robotic agent might have like cameras and infrared range sensor to sense the stuff from the environment and use the different type of motor to use as an actuator to change the environment. Okay. And also we got the software agent, something like that. Yeah. So this is our example. Okay, so the fundamental faculties of intelligence or the intelligent agent are that they must be having the abilities of sensing, which is the sensor, the acting, which are the actuators, and the ability to understand, reason, and learn. Instead, they must have the ability to understand and reason and learn from the percept which they get from the environment. Okay, because if doing something blindly is not actually a character, it's not intelligent. Okay, even if you get a lot of sense, a lot of stuff from the environment, a lot of percepts, if you don't understand what is actually meaning, it's useless. Okay, you need to understand what is the percept doing to make use of it and carry out the action. So this is what an agent should be having. Okay, so next part, and this is the performance of the agent. Okay, so our behavior and performance of our intelligent agent in terms of agent function are actually the perception history to action mapping. Means that we need to have a very good action mapping based on our perception history or the perception sequence. Okay, and the ideal mapping is that to specify which action an agent ought to take at any point of time. Instead, the best stuff the agent can do at that particular time. Okay, and the performance measure is actually a subjective measure to characterize how successful an agent is. For example, to measure the performance of our intelligent agent, we can measure it by using many different of the aspects. For example, the speed, the power usage, the accuracy. In the case of like the vacuum cleaner, we can measure its performance measure by using like the speed, like how fast it can clean out all the stuff, like how lower the power usage can use. If the lesser the better, right? And the accuracy and the for example, like the clean, like how clean the environment after the vacuum cleaner clean out. So this accuracy and the cost and how many costs it takes, something like that. So this is a performance measure. So how to measure the performance, okay? So for example, our vacuum cleaner agent. So this is our example of an intelligent agent, okay? So in this case, we have the percepts, actions, and the agent function, okay? So you can see, for example, you can see in this table, in this diagram, this is our vacuum cleaner, okay? So right now it's at the at the location A, this is location B. So these are the rubbish located on the floor, okay? So in this case, the percepts are actually location A and B and the content, dirty or clean. And the actions that the agent can perform are go to the left, go to the right, and suck the rubbish, and on no operation if like all clean, something like that. Okay. So let's see the table for more gain and acceleration. So for example, if the percept is actually A and clean, means that the agent is located at here. So if the case is that if the A is at A and the floor is clean, then the agent will proceed to move to the right. Okay, move to the right. And if the A is dirty, then it will perform to suck the rubbish. Okay. So this is the same case applied to B lah. If the cleaner is located at B, then if the B is clean, then we go to the left, and if the B is dirty, then it will clean up the floor. Okay. So if the process sequence is like this, like A clean and A clean, then will go to the right, and if the floor is actually clean, at first the vacuum cleaner is at here, and the floor is clean, right? So in the process of like it will go to the right, right? So at the process of moving to the right, if the floor like if you throw rubbish on the floor at that particular time, and the floor becomes dirty, then you will proceed to clean the floor again. So this is actually how it works. Okay, it will take the action at any particular of time if given the percept. Okay, so this is example of the vacuum cleaner agent. So okay, so at the additional, we are come to the part of the concept of rationality. This is very an important aspect for the intelligent agent, because that an agent which is rational should actually strive to do the right thing at the right time based on what it can perceive and the action it can perform. Basically means that the agent, if a agent is rational, it should do the best action that it can perform based on the stuff it perceives from the environment. So it means that doing the right thing at the right time now, okay? And if the agent do the right action that we will call, then the action is successful, means that the agent is success, okay? For example, the performance measure of a working cleaner agent is the thing that I talked about just now. Is actually like the amount of dirt cleaned up. The more clean up, the better the agent, right? And the lesser amount taken is the better, right? And the lesser amount of electric consumed is better, right? And also lesser amount of noise generated. So this is how we measure the performance measure of the vacuum cleaner agent. Okay. So in the rationality case, firstly we have come to a part of the term which is called perfect rationality. Okay. In this case, we assume that the agent is omniscience, means that it knows everything and will take the action that maximizes the utility. But in this case, this is actually impossible, because it's impossible for the agent to know everything that it requires to know, and also to do the best thing that maximizes the stuff. So it's actually quite impossible. So that leads to our second case, which is the bounded rationality. This is because of the limitation of many aspects. For example, like our human mind is have a lot of limitation, where we cannot do a lot of stuff in the same time, right? And also, we not always do the best decision based on the environment, because we need to do the best decision, right? We need to consider all the possible scenarios one by one, and then pick out the best one, and which will consume a lot of time, right? And so means that we cannot have the perfect rationality due to many constriction, okay? So ours are the bounded rationality, okay, due to many constraints. Okay, so let's come to one part, which is the rational action. So a rational action is the action that maximizes the expected value of the performance measure given the percept sequence to date. Means that agent, if the action of an agent is rational, if it is able to maximize the expected value of the performance given the percept sequence. Okay, so means that if an agent is rational, means that it can do with the best of its knowledge and to the best of its abilities with the existing constraint. Yeah. So this is what an agent, if it's possible to carry out the rational action. Okay. So rational action means that they can use the extent of the best of the knowledge, what it perceives from the environment, and do the best of its abilities. Means that carry out what action is given to perform. Means that it can do the best of all its stuff. Means that the action perform the rational action, okay, with the constraints available in the environment. So this is called the rational action. Okay, so for each possible percept sequence, an rational agent should select an action that is expected to maximize its performance measure given the evidence provided by the percept sequence and whatever built-in knowledge that agent has. Means that a rational agent should actually select an action that is expected to maximize the performance measure for each possible percept sequence given the percept sequence and whatever built-in knowledge it has. Okay, so it means that the rational agent should actually maximize the performance measure by using the percept sequence, and you carry out the action that is available to carry out. Okay, so for example, this is the rationality of an agent. For example, the performance of the agent, and also the agent's prior knowledge of environment. So what does it mean? For example, for the vacuum cleaner agent, okay, for the vacuum cleaner agent, if the prior knowledge of the environment is good, then it can maximize its rationality. For example, if there is some part of floor which is black, right? So the agent might consider the part of the floor which is black is dirty, so it might waste more time or use some time to get out or something like that, which will cause it to be not rational. So if the knowledge is given to the agent Like for example, if you already tell the agent that this floor is black, so don't go to like clean it if it even is black, something like that. So okay, so if the agent have the prior knowledge of the environment, so it can perform the action more efficiently, increase the performance of the intelligent agent. Okay, and it actually the rationality of the agent is actually also based on the actions that the agent can perform. Okay, for example, you cannot call an agent to do the stuff which is unable to perform, which is restricted, constrained by its like actuators. For example, you cannot call an agent to fly if you don't give it the wings, right? So this is what the action that agent can perform. So we can like also increase the rationality by increasing lessing the like decreasing the restraint that agent is having. Okay, and also the agent's process sequence to date is also one aspect of the rationality. Okay. Okay, so right now we come to another part. So omniscience is the concept that everything is known. Okay, so rational is different for that because the process sequence from the agent is not always the all relevant information that it can get. Because for example, the card game, even you have the eyes, right, you cannot know the cards of the others. You can only see the cards of yours. Okay, is that you cannot know everything that you need to know. So this is a constriction. And also the rational is different from being perfect because rationality only maximizes the expected outcome by giving on the given percent sequence. Okay, so on the percent sequence, it can only maximize the expected outcome on the percent sequence, while the perfection is actually mean that you know everything and then you maximize the actual outcome. So that is different, right? It's different. It's a different stuff because you cannot achieve perfection for the agent. Okay, it's not possible. And you can see this is a definition of the omniscience. And yes, the rationality is distinct from the omniscience. Okay, it's two different stuff because it's impossible to achieve that. And also, so in the case of that, it's different for that, so that the agent can actually you perform an action in order to modify the future percepts so as to obtain the useful information. Instead, the agent, in order to like achieve to like in order to achieve to near to the near to the level of the omniscience, the agent need to gather more information from the environment, like so the agent can actually perform action to modify the feature aspect to obtain useful information. So this is how the agent can do in order to obtain more information to achieve the level like the omniscience, but it's very hard. Okay, and also a rational agent should actually be autonomous, as for example, by actually having the ability to learn and adapt from its own experience and determine its own behavior. So this is what we call an rational agent. Okay. Okay. So that's all for my part, and now I will pass the mic back to our lecturer, Steve, to continue the continued session. Okay. Thank you very much.
All right, so thank you, Mr. Ningui, for the first part of today's lecture. So now let's take a short 2-minute break. So you can go to the toilet or have a water break, or just take time to digest what you learned just now. All right, so I'll set a timer for 2 minutes, start from now. If any of you have any questions from the first part of today's session today, feel free to ask in the chat box. All right, so I hope you get your water break or your toilet break already. So now let's jump into the second part of today's session, which will be peas, Peas, not that kind of peas, not the green peas that you eat. All right, peas here. PEAS stands for performance, environment, actuators, and sensors. Pun not intended, yes. Um, so what this is actually, it is actually a model or a method used by, well, AI designers to specify the setting for intelligent agent design, right? So say you want to design an automated taxi driver, or in today's context, an automated Grab driver, whatever you want to call it. Um, you would use Peas as a tool to help you design an intelligent agent in terms of the performance, right? So we learn some of these new terminologies in the first session. So performance measure, environment, actuators, and sensors. We learned about the definitions in the first session, but now let's go into how we actually apply it in this model. So here is a table made based off the piece model. So you have the agent type or the agent. You have the performance measure, environment, actuators, and the sensors, right? So as mentioned earlier, we have the automated taxi driver. So the first part here, the performance measure. Uh, think of it simply as how would you rate a Grab driver uh, to give them 5 stars, or how would you rate them to give them 4 stars, 3 stars? Performance measure. So here we have how you would measure the performance of a taxi driver. So how safe is the taxi driver driving? How fast was he going? Is he driving legally? Does he abide by the traffic rules? Are you comfortable during the trip? And does the taxi driver maximize profits from, well, doing its job, right? So performance. Now the next part here is the environment. So environment is basically where the agent would work in, so its surroundings. So obviously the taxi driver would drive in roads, and on those roads there will be other traffic, so other vehicles, other cars, motorcycles. Of course, the taxi driver also have to watch out for incoming pedestrians, and also have to take into account its customers, the one they're driving for. Now, actuators. Um, the tools that the agent uses to do its actions. So one could argue that the actuators for a taxi driver would be a car, right? The car the driver drives. But to be more specific about it, it would be the steering wheels, the accelerators, brakes, signal, horn, and display. Now, as sensors, how would the agent perceive its environment? So you have the cameras as to provide visual. You have sonar to provide like an ear-like perception. You have the speedometer, GPS for location, odometer, accelerometer, engine, sensor, and keyboard, right? So this is how would you use the piece model to design um, an ideal taxi driver, an automated taxi driver. Now here there are 3 more examples over here. You have medical diagnosis system, part picking robot, an interactive English tutor. Let's choose one that is most likely to be more simpler to explain and understand. So here I have an Excel sheet over here, which I copy the table from the slides. So let's do the piece model for a part picking robot, right? So if you don't know what a part picking robot is, it's this thing. You might see it in like commercials, like for factories, right? So let's first analyze this particular robot. So you can see here, let's just assume that this particular robot is working in a factory, right? Then what y'all can see here, you have these robot arms, right, to pick up the items, and you have a camera here. So this robot arm is what we consider as the actuators. So let's just type in here, actuators, robot arms. Then you have the camera over here to perceive its environment, to see what's around, the robot, right? So you have the camera as its sensor. Now, the environment, you could argue that it is working in a factory, but let's be more specific about it. So what are the possible elements in that particular environment? So in this picture, there's actually a conveyor belt over here that moves these bins of items around so that the robot could pick an item from each bin to be packaged into a box, right? So that's one element of the environment. So conveyor belt. Conveyor belt. And you could say that there are other factory workers over there. So that could be an element inside the environment column. So now let's talk about the performance measure. How would you measure the performance of this particular robot? So let's analyze its task. Its task is to pick one item from each of these bins to be packaged into this particular brown box, right? So you might think that, okay, this robot might make mistakes, might malfunction. So that could be a measure to check its performance. So you could say that the performance measure over here is number of items put in correctly. You could say the number of items or the percentages of correct items. So that's two ways of how you could measure this part picking robot's performance. Now let's go back into the slide. As for the medical diagnosis system and interactive English tutor, I might leave it to you as a food for thought. But if you have any questions, you can just ask. So now let's go into environment types. There's actually a lot of types of environment that an agent could be working in. So here I'll explain this in a series of comparisons. So these two are inherently opposites of each other, right? So you have the versus here. So let's go into the first comparison, a fully observable environment and a partially observable environment. Now, is everything an agent requires to choose its actions available to it via its sensors? In other words, is the information perfect or full? If it is so, the environment is fully accessible, or you could call it as fully observable. If not, parts of the environment are inaccessible. Hence, we will call it as a partially observable environment. So, if the parts of the environment are inaccessible, then the agent must make informed guesses about the world that they're working in. In decision theory, it's perfect information versus imperfect information. So here is a remark of an agent sensors. All right, so the agent sensors give it access to the complete state of the environment at each point in time. So every second, every time, the sensors have to give the information to the agent to as the perception, right? As the information that the agent would use to determine its next action. Right. So let's talk about the examples. The example of a fully observable environment here would be a chessboard, right? So let's go to a chessboard, right? So I can safely say that, okay, maybe some of you have played chess before, and you can see here the environment, you can fully observe it, right? You can see all the chessboard, all of your opponent's chess piece as well as your own, right? There's nothing hidden here. So we will call this as a fully observable environment. Now, what about a partially observable environment? Some of you may know this game, a card memory game. Maybe you would call it a concentration game. So in this environment, this whole set of cards are actually facing down. So the information is actually incomplete to the agent. So to gain information, the agent has to play the game, flip the cards one by one to gain more information, and then to determine its next course of action. Hence, we will call this as a partially observable environment. Now, the next comparison we'll talk about is deterministic versus stochastic. Now, in a deterministic environment, it is fully determined by the parameter values and the initial conditions, when a uniqueness in the agent's current state completely determines the next state of the agent. So an example of this would be, again, chess. There would be only few possible moves for a chess piece at the current state, and these moves can be determined strategic, right? If you don't understand what that means, okay, let's go back to the chessboard. So let's just play with the computer here. All right, so I'm just going to move a random piece, okay, right now. All right, let's examine this state, right? So deterministic, you can like determine what's your opponent's next moves because there are only like so few, a few of the pieces that I can actually move in this current state. So let's say the opponent is the opponent would be expecting me to move either these pawns over here or the queen here or the okay, actually that's it, I think. Sorry, I don't play chess that much, but the opponent would not expect me to move this piece, right, the rook, because in its current state the rook won't be able to move it around. right? I can move this rook around. So this uniqueness, right? So this explains the second point here. When a uniqueness in the agent's current state completely determines the next state of the agent. So I can actually move this. So all of these are deterministic elements. Let's talk about a stochastic environment. It possesses some inherent randomness. In a stochastic environment, it is random in nature, which is not unique and cannot be completely determined by the agent. So an example of this would be self-driving cars, right? So you can imagine in a self-driving cars, the environment around it. There are many elements around in that element that are random. So you wouldn't be able to tell if the weather is good. I mean, you can't predict the weather. You can't predict whether or not that one particular car would hit you or not. You wouldn't be able to like determine also if suddenly there's a pedestrian just run to the street, right? So yeah, that's the randomness that we're talking about here. It is random in nature and not unique and cannot be completely determined. Right, so the next one is episodic versus sequential. An episodic environment is where each state is independent of each other. The action on the state has nothing to do with the next state. There is a series of like one-shot actions, and only the current percept is required for the action. So a real-life example here would be a support bot, a chat bot, answer to a question and answer to another question, and so on. So each question and answer you can count as a single episode. Let's go to a chatbot example. So the chatbot that I think most of us will be familiar with would be something like an AirAsia chatbot. So Ava here is the chatbot. So I would typically use this to like check my flights and maybe to process a refund, right? So this is the predefined message by the AI chatbot. Okay, so here it has given me like a series of choices that I can choose. So it is asking me a question right now. So I'm just going to choose flights. All right, so then it has prompted me to choose another option. Let's choose book a flight. All right, so let's stop here. Okay. All right, so let's just look at here. So this question and answer over here is a single episode. And then this question and answer session here would be another episode. So that's what we call as an episodic environment. Now, as for sequential environment is where the next state is dependent on the next action. The agent's current action can change all of the future states of the environment. And the agent requires memory of the past actions to determine the next best action. So a real life example here would be playing tennis or playing badminton, where a player observes the opponent's shot and takes action. So if you played badminton before or you played tennis before, say your opponent is the opponent hits a high arc ball, right? So you have the choice to either smash the ball or you could do a trick shot. So Basically, what you're doing is you're observing your opponent's shot, and then you would decide the next action that you want to take. So this is what sequential environment means. Next, static versus dynamic environment. Static, as the name suggests, is completely unchanged, while an agent is perceiving the environment. Easy to deal with because an agent does not need to continue looking at the environment while deciding for an action. So an example here would be cleaning a room by a dry cleaner robot, which is the agent. It's an example of a static environment where the room is static while the robot does the cleaning, right? So you can imagine in your own room, there's a robot that moves around and cleans your room. So the room itself would not change in any shape or form while the agent is doing its task. So that's static environment. Now, how about dynamic environment? The environment could be changed while an agent is perceiving the environment. Agents keep looking at the environment while taking action. So example over here would be playing soccer, where the player's position keep changing throughout the game, right? So you would need to like constantly observe where your opponent's players are to decide whether you want to shoot the ball to the goal or you want to pass it to your teammate, right? So that's a dynamic environment. Now, a discrete versus continuous environment. For discrete, it has a limited number of distinct states, clearly defined precepts and actions. It also has fixed locations or time intervals. It consists of a finite number of states and agents have a finite number of actions, right? An example for this would be in a tic-tac-toe game, right? You have only like 9 boxes that you can choose. And out of those 9 boxes, you can choose like only 3 to 4 because your opponent also has to choose like 3 to 4 boxes to fill in. So that's an example for a discrete environment. Now, for a continuous environment, it could be measured quantitatively to any level of precision. It can have an infinite number of states. The possibilities of taking an action are also infinite. Real life example to this would be in a basketball game, or you could say the same thing about the soccer game earlier. The position of players or the environment keeps changing continuously, and also hitting the ball, or you want to dribble the ball or shooting the ball towards the basket can also have different angles and speed. Hence, it has infinite possibilities, right? So let's say you're shooting a ball towards the goal. You have many angles that you can take, and you can apply different levels of strength to shoot the ball towards the goal. So that's continuous environment. Now, the last types of environment would be single agent versus multi-agent. As the name suggests, a single agent is essentially an agent operating by itself in an environment, or there are multiple agents working together. So basically, is it agent working alone, or is the agent working with other agents? That's basically it. Here's the summary of like different types of tasks and what are the environment, the types of an environment that they are in. So for example here, let's take the example earlier for the part picking robot. Is it fully or partially observable? Now here we call it as a partially observable because the sensors built for the robot are actually only used for looking at the items that the robot is going to take. It's not designed to observe the 360 view around it. It only looks at a certain point, a certain field of vision for the robot? Is it deterministic or stochastic environment? We would say that it is stochastic because there are random elements in that environment. So working in a factory, you would think of there would be accidents happening, maybe a blackout, maybe someone tries to rob a factory or something. So it is completely random. It is episodic or sequential. We call it as episodic because, okay, take one item and put it into a box. Is one episode, right? It is independent. The episode before does not influence the next episode. That's why it is episodic, not sequential. The previous action does not influence the next sequence of actions. Is it static or dynamic? It is dynamic because you have the conveyor belt that's constantly moving to move the box, to move the bins. And is it discrete or continuous? We would consider it to be continuous because there are many ways that the robot could go wrong, right? Maybe the robot might be off, like off like 1 cm or 2 cm away from the box. Then is it working alone or working with others? So in this case, from that picture that I showed you earlier, it is working alone. So it is a single agent. Right, so that's the end for part 2 of today's session. So let's have another 2-minute break to let you guys have a water break or a toilet break. And if you have any questions about the second part of today's session or from the first session, the definitions and terminologies, don't be shy to ask in the chat box. Right, we have our fellow tutors here ready to answer your questions. All right, so wow, the timer stops and it beeps in my earphone. All right, so 2-minute break is up, right? So we hope you already had your short water break or toilet break, right? So now let's move on to the third part of today's session, which will be presented by Ms. Arbota. So Ms. Arbota will be taking over from here.
All right, can you guys see my screen?
Yes.
Okay, so hello people. So in this part of the lecture, we will learn about the basic structure of intelligent agents and also some different types of agents. Okay, so let's start with the first one. So basically, an agent can be described in terms of the agent function, right? So the role of agent function is to map every possible percept sequence, which simply means perceptual inputs to our agent, to the possible actions that our agent can perform as described in this function, right? So what I mean by this is we can basically say that an agent's behavior is completely described by this agent function, okay? So in its simplest form, the structure of an agent can be described as a combination of two things. Well, the first one is architecture. Now, architecture refers to like devices or machinery that our agent executes on. For example, it can be a personal computer, it can be a car or a camera. So the next is an agent program is actually an implementation of the agent function that we just described. So what I mean by this is, as we have just learned, agent function is actually is an abstract mathematical description, right? But the agent program is actually a concrete implementation of that function, and it runs within some physical device or software. Okay, so yeah, we can basically see that the task of artificial intelligence is to design an agent program that implements agent function. Okay, so let's take this vacuum cleaner as an example. So what is the function of this vacuum cleaning agent? So this 3 lines of instructions here we have can be basically considered as a function. So the function of our vacuum cleaning agent is to clean the floor. So if the current location is clean, then it will turn right or left and so on, right? But the actual act of actually cleaning the environment and performing that operation can be understood as an agent program. Okay. Okay. So in principle, there are 5 types of agents. The first one is simple reflex agent. The next is model-based and goal-based and utility-based, and finally, learning agents. So agents are classified into these 5 categories based on their degree of intelligence and capacity. Okay, now let's look at those one by one. So the first type of agent is simple reflex agent. Well, as the name suggests, simple reflex agent is very simple. It only operates based on this condition action rule, which is if else statements, right? So one characteristics of a simple reflex agent is that it only takes account what the world is like right now. It only considers that, and it performs its actions only based on that input. So here are some characteristics of our simple reflex agent. So as it's very simple, it has only very limited intelligence, right? And the next thing is it performs its actions only depending on the current input, not on the historical data, right, as described in here. So for example, in this example of a vacuum cleaner, let's say this vacuum cleaner agent is a simple reflex agent. So if it's a simple reflex agent, it only takes account what the current situation is like, right? So it only considers if the current location is clean or dirty, and it doesn't care about whether this location was dirty like a month ago or if it was dirty yesterday. So yeah. So as there is no need for storing the historical percept, there is no memory requirement for this simple reflex agent. But there is one possible problem associated with this approach. So let's say if the environment that our agent is operating is not fully observable, there is a possibility of being stuck in an infinite loop. So that vacuum cleaning agent example that we just described. So in this example, right? So let's say it doesn't observe its current location fully. It only have partial information about its location. So what it does is it only based on this function, it only it only wants to know if the current location is dirty. If it's not, then it will turn right. And if the location B is also not dirty, it will turn left. So it will keep doing this because it doesn't know the locations that it has cleaned already, right? So it has the problem of being stuck in an infinite loop. So it will be just like a fly buzzing around window or light, right? So, but there's actually a solution to that. One possible solution is to randomize its sections. So in case of a vacuum cleaner, we can just say that, well, randomly analyze some place locations. If all of them are clean, then you can stop your operation or something, right? Now, okay, let's move on to the next one. The next one's model-based agent. The model-based agent also operates based on the condition action rule, but the one difference is that it actually has an internal memory to store information about how the world is evolving and what effects does my action have on this evolution process of the world. So it means it has memory requirements, right? Yeah. So characteristics of model-based agent is that it can keep track of the parts of the world that cannot be seen, and it also maintains some sort of internal state, which is the historical data, depending on the possible. So as I said before, it will know how the world evolves around it. So an example would be, let's say we have an agent that its task is to drive. So a driving agent, if the driving agent was a model-based agent, right? It will know if the car is approaching from its behind, and it can alter its actions based on that information. So if the agent decides to turn its wheel clockwise, and it knows that it will eventually take it to the right direction, and it will know that this action will affect the world somehow, right? Yeah, so that's it. So the next one, we're going to talk about the goal-based agent. So goal-based agent is also quite similar to the model-based agent, but the one extra thing is it has just goal information to guide its actions. So basically it has a goal to reach in mind, and it performs its actions based on that, and this goal will be kind of like a performance measure for deciding whether it has reached its destination, or how well it's performing, or how far it is from its goal, right? Yeah, so, well, let's say if we have a taxi driving agent, the functions of a taxi driving agent is R to drive left or right or straight, right? So, but if it was not a goal-based agent, so what is the point of driving left or right or straight if it doesn't have any goal to reach or destination to reach, right? So, knowing only the state and environment, it's not enough to make the agent succeed. So, as for the goal-based agent, it has a goal in mind, and which is basically a destination to reach. So it uses this information about a goal to guide its actions, and it basically analyzes how far it's from its goal, and it has to do a lot of planning and searching ahead, and it has to consider all the possible actions to take in order to guide its actions. Okay. So yeah, it uses goal information. Goal information is kind of like a situation that is desirable to be in. So this goal-based agent desires to be in that state. Okay. Okay. So utility-based agent is a little bit different than the goal-based agent. So one difference is it has an utility function to define its actions and measure its actions. So just like the goal other agents, it also has a memory requirement to store how the world's evolving and what are the effects of its actions. But it also takes into account like how well, for example, in this example, right? If in this example we have an utility function which is happiness, so it will consider how happy I will be if I reach this state, or right. So yeah, so it will decide its actions based on that input. So yeah, goals are not enough to generate a high quality behavior, especially in some cases, right? So the use of utility function is to map its performance to real numbers to describe its degree of success. For example, just like in this example, if our utility function is happiness, right? So it doesn't consider whether it's happy or unhappy. So it's not like binary feedback. So it considers how happy is it. For example, is it 90%? Is it 70%? Or so if it's if the utility function is success, so if the current state is, so it considers how successful is the current state, right? Yeah, so the complete specification of the utility function will help to make rational decisions. Yeah, so utility-based agents are used when there are several desirable outputs, and we want to know which one is the best to go, right? Okay. The next and the last one is about learning agents. So learning agent is actually a little bit different than other agents. So learning agent has 4 components to guide its actions and measure its performance, right? So let me first talk about what is a learning agent. A learning agent is a type of agent that has a learning capability, or it can learn from its past experiences, right? So it can also adapt to this situation quickly. So what it means is it will start its performance with a very basic knowledge, and it is able to improve and adapt through this process of learning. Okay, so here we have a description of all these elements. So the first element is learning element, which is responsible for making improvements and basically to learning from its past experiences. And it takes some sort of performance standard to begin with, and it desires to reach or surpass that standard. Okay, so next one is the performance element. So performance element basically helps this agent to select external actions to improve its performance. So yeah, so it kind of like provides knowledge, information about knowledge or chance, right? The next one is probably the most important one is the critic element. Critic element basically is kind of like a judge to this learning agent, and it desires to fix the performance of the learning element and to provide some feedback to how well it's doing, right? Then the last one is the problem generating agent, and it's responsible for suggesting actions that will have new or informative experiences. So problem generator will tell the learning element if it has reached its goal or not, or what can it do to improve its further performance, or what new inputs can it take. Okay, so here we have an example of a taxi driver as a learning agent. So if the taxi driver was a learning agent, right? Let's say it doesn't know anything about its environment initially, but it desires to improve its performance through learning. So in this case, right, performance element will describe how well it's currently driving. So performance elements can be, for example, like safety, or how well it's driving, or it's driving legally, right? So let's suppose a case: a taxi driver decides to make a turn left across 3 lanes, right? So as you consider, that is a very dangerous situation. So in this case, critic element observes the shocking language, or like negative reaction from other drivers or passengers, and it will inform the learning element that basically kind of like, hey, that was not a good action to take. So learning element considers this feedback, and it tries to modify its actions for the future cases. And the problem generator element also like suggests things like, well, you can try your brakes or something, right? So yeah, so there's actually some problems with that, which we will talk about now. So exploration means that exploration basically must be carried on in initially unknown environment, right? So just like the learning agent, it doesn't know anything about its environment initially, but it tries to explore its environment, right? But there is a possibility of that exploration process turning into exploitation, because learning experience can be very costly in the short run, especially, for example, if you want to implement it for a taxi driver, and it also has bad experiences, right? Like shocking language from other drivers, or like has very very little wage or fewer passengers and so on. Yeah, so so experimenting with learning agent can be very costly or difficult in the short run, but it's definitely very productive and beneficial in the long run, right? Yeah, so basically that's it for today's part. Do you guys have any questions regarding the types of agents?
Or if you guys have any other questions from the other parts of today's session, you can ask now.
All clear, guys, and thank you for joining us. This was our third session of the AI Part 2 about the AI Intro Part 2. So basically what you learned today was AI through some new definitions. Basically AI as an independent agent in some senses. So it's able to basically try to mimic your actions in a more physical sense. It's able to perceive the world around it and refer to a logic, and basically based on those informations make an action, same as you guys. Basically you see the laptop, you refer to a logic, basically your way of thinking, and then you make an action, basically ask us a question or say all clear, something like that. Okay, okay, thank you for sharing the summary, Steve. Thank you. You guys can refer to this short text as well. It's pretty brief, concise, save your time, and captures the essence of the session as well. Are you guys clear on what went on today? Any questions, guys?
So a short announcement here. Right. So another gentle reminder to all of you that the materials are already available on our Project J website, and the recorded video for today's session will be uploaded on YouTube within a few days. And also, don't forget to follow all of our social media, so Instagram and definitely YouTube. Like, share, and subscribe for the contents that we uploaded. All right. So, Ace, do you have anything else to say?
Nope, that's all for us. If you guys have no question, and thank you for joining us, and have a nice day and a nice weekend.
All right. TGIF tomorrow, guys. So, yep. Thank you for joining us.